Here's a crisp countdown of the 5 deepest vertical holes humans have drilled, ranked by true vertical depth in feet, not the total measured length some zigzag wells boast. From scientific quests to oil exploration, each of these descents pushed people, machines, and materials to their breaking points. Number 5. KTB Borehole, Germany. The German Continental Deep Drilling Program, better known as the KTB, punched approximately 29,860 feet straight down into the crust of Bavaria to study how our planet is put together. Engineers battled extreme heat, crushing pressures, and rock that grew steadily more abrasive the deeper they went, shattering any hope that drilling would get easier with depth. The KTB wasn't about striking oil or gas. It was a pure science mission designed to gather data about temperature gradients, fluids, and the way seismic waves travel through real rock. Along the way, the team refined downhole tools, drill bit designs, and logging methods that would later seep into industrial practice. Even the steel of the drill string had to be carefully chosen so it wouldn't twist like licorice or snap under torque. The borehole delivered a trove of petrological samples, revealing fractures and fluid pathways far deeper than most geologists expected. Though they planned to go deeper, the compounding technical hurdles and budget realities eventually called time on the project. What remained was one of the best X-rays of continental crust ever assembled, plus a giant leap in deep drilling know-how. KTB's legacy runs beyond depth records. It's a playbook in how to manage risk when the unknowns multiply with every foot. Heat management, for example, became a constant chess match. Circulating drilling mud had to carry heat away without losing viscosity or destabilizing the wellbore. The team also learned how microcracks and fluids complicate predictions because real rock rarely behaves like the tidy diagrams in textbooks. Every trip of the bit demanded careful planning to avoid stuck pipe and costly fishing operations. Even the simplest choices, like the weight on bit and rotation speed, had to be tuned to a hair's breadth to keep progress steady. The project taught industry and academia how to interpret high-pressure, high-temperature logs without fooling themselves. And perhaps most importantly, it showed that a well designed primarily for science can pay off across the board, advancing materials, science, geophysics, and drilling engineering in one audacious shot. Number 4. Bertha Rogers Borehole, USA. With a depth of approximately 31,440 feet and drilled in Oklahoma's Anadarko Basin in the early 1970s, the Bertha Rogers well set a depth benchmark for its time and delivered one of the most famous drilling surprises in history. As the bit chewed its way down, temperatures rose and pressures mounted, turning routine decisions into make-or-break calls. Then came the twist. The well encountered molten sulfur, which quickly cooled and cemented parts of the string, derailing plans and equipment alike. That bizarre event became legend, a reminder that underground geology can swerve from the script with little warning. Even without the sulfur, the usual rogues gallery, lost circulation, torque and drag, and bit wear, shadowed the operation at every stage. Crews continually re-optimized mud weights and additives to balance well control with borehole stability. By the time they halted, Bertha Rogers had proven both how far technology could stretch and how easy it is for nature to stretch it further. Operationally, Bertha Rogers helped define best practices for coping with extreme downhole conditions long before modern digital tools were common. Engineers learned to trust, but verify, every gauge, because instrument drift at high temperature can lead teams astray. They built redundancy into measurement and control systems, so one dodgy sensor wouldn't dictate an expensive mistake. The sulfur incident also sharpened emergency procedures, making crews faster and calmer when plans went sideways. Lessons from the metallurgy of drill collars to the chemistry of mud systems filtered into later deep efforts all over the world. The well's story is a case study in resilience. Progress wasn't linear, and victories arrived one stubborn foot at a time. Even after the bit stopped turning, its data and war stories kept shaping how the industry thinks about the deep unknown. Number 3. Tiber Oil Well, Gulf of Mexico. The Tiber prospect, drilled in ultra-deep water in the Gulf of Mexico, holds the offshore record for true vertical depth. an accomplishment that demanded precision across two brutal frontiers, the ocean above and the rock below. Before the bit even touched bottom, engineers had to navigate thousands of feet of water with tight positional control, subsea equipment, and a riser system that behaves like a giant, flexible straw. Once in the formation, every decision, from casing seat to mud density, balanced a razor-thin margin between kicks and lost circulation. The geology stacked challenges like pancakes, interbedded layers with different strengths, pressure regimes that changed abruptly, and temperatures that punished tools. High-spec drill bits and motors were cycled with surgical timing to preserve performance at depth. Downhole measurements provided by logging while drilling tools were the team's eyes in the dark, constantly updated to keep the borehole on target. With a depth of approximately 35,060 feet, Tiber's descent proved that offshore wells can go toe-to-toe with onshore depth records when planning and technology collide just right. The operation also highlighted how modern deepwater drilling is really systems engineering in disguise. Station keeping relied on dynamic positioning that continually finessed thrusters against currents and wind to hold the rig almost motionless above a pinpoint on the seafloor. Subsea blowout preventers had to function flawlessly despite brutal pressures and the need for remote control and testing. Fluids engineers crafted mud recipes that would carry cuttings efficiently up a very long annulus without eroding equipment. Vibration and whirl, silent killers of drill string health, were monitored and mitigated with downhole shock tools and smarter drilling parameters. Every trip, connection, and test was timed to reduce non-productive hours because costs skyrocket offshore. By the time Tiber reached its target depth, it had stitched together a masterclass in coordinating people, physics, and machinery at the edge of what's possible. Number 2. Shendi Take-1, China. Shendi Take-1 pushes onshore, drilling into territory once reserved for headline-grabbing offshore projects, driving nearly 36,000 feet, approximately 6.78 miles, down into the Tarim Basin. The basin's notorious for its hard, abrasive formations and wide temperature swings, which turn drill bits into consumables and drilling schedules into suggestions. Engineers fought cuttings transport problems that get much harder as the hole deepens and angles stack up, even when the well is kept vertical. High-temperature electronics had to survive long enough to deliver the downhole telemetry essential for decision-making. Lubricity additives and carefully tuned mud rheology became heroes for controlling torque and drag. The casing program, each steel string that lines and protects the hole, was planned like a chess match, anticipating what the rock would do long before it did it. When Shendi Take-1 hit its depth milestone, it signaled that onshore rigs, when properly spec'd and crewed, can chase the very deepest targets on Earth. From a technology perspective, the well stitched together advances that didn't exist when the earlier records were set. Polycrystalline diamond compact PDC bits with better cutters and heat management held sharpness longer, reducing the number of trips and the risk each trip introduces. Real-time data, streamed topside, made it possible to adjust weight on bit, rotary speed, and mud density on the fly without guessing. Enhanced solids control equipment kept the mud clean, maintaining viscosity and density, even after days of continuous drilling. Metallurgy improvements let drill pipe endure higher torsional loads without fatigue failure. Logistics mattered too. Spare parts, specialized personnel, and contingency equipment had to be staged with military precision across a remote, sprawling landscape. The achievement wasn't just a number on a depth report. It was proof that modern onshore operations can integrate cutting-edge tools, data, and discipline to tackle world-class depths. Number 1. Kola Superdeep Borehole, SG3, Russia. The Kola Superdeep remains the deepest vertical hole ever drilled. So deep that if you stacked more than 14 Burj Khalifas end to end, you'd still be short. Beginning in the 1970s, the project had a simple, radical goal: drill as far down as physics, geology, and human stubbornness would allow. As the bit pushed past 20,000 feet, everything got harder at once. Temperatures soared, pressures climbed, and the rock began to flow and fracture in ways that defied models. Tools cooked, sensors drifted, and electronics that worked in labs failed in the borehole's hellish environment. The team chased countless gremlins, stuck pipe, borehole collapse, and even the slow creep of rock closing in on the wellbore. Yet foot by foot, they kept at it, redesigning components and rethinking strategies as they learned. By the late 1980s, Kola is approximately 40,230 feet deep, rewriting what humans thought was possible under their own feet. Scientifically, Kola was a treasure chest. Core samples revealed fracture networks and fluid signatures that changed how geologists think about the deep crust, more porous and dynamic than textbooks suggested. The project also captured microscopic fossils at surprising depths, sparking debates about how surface materials get carried downward and altered over time. Seismic predictions calibrated against real rock data were updated, improving everything from earthquake models to exploration geophysics. On the engineering front, Kola forced innovations in high-temperature drilling fluids, logging tools, and bit technology that still echo in modern designs. It also taught humility. Past a certain depth, rock isn't just harder, it behaves differently, and the rules need rewriting. When the final tally was taken, Kola didn't just set a record, it laid a foundation for every deep drilling effort that followed. Its depth marker, about 7.62 miles, still stands as a gauntlet for the next generation of drillers to pick up. Thank you for watching. If you enjoyed it, please like and subscribe. Until next time.